And it is recording. Okay, what can I help you with?
Mister, I still don't understand anything from gases. Since the first semester, I keep confusing gases.
Gases? Okay. How does a hot air balloon work?
When you add heat and I guess pressure, it inflates, and the more of that, it helps it go up.
Okay, that's correct. What happens when you squeeze something?
You add the pressure and it pops
Why?
because all the molecules inside are getting suppressed together.
What happens to the size?
The sides they get together. The sides get together.
Okay, so that doesn't answer my question. What's the size?
So
what does that mean, though?
what does that mean?
What you just said, because you didn't answer the question.
What was the question?
What happens to the size?
The sides?
Yeah. Like, if I were to squeeze this box right now, what happens to the size? You didn't answer it.
The size stays the same.
If I squeeze this, it's going to stay the same?
No.
You just said yes.
Mister, the sides or the size?
The size. Well, it doesn't matter, actually.
Because I heard sides, so I was like, huh?
Well, it doesn't matter. It's the same answer. The sides are directly proportional to the size.
So if you squeeze it,
It gets
smaller.
That's what I'm looking for. Proof, right? Am I squeezing it right now?
Yeah.
Yeah, and the pressure right now you can see is 11.6. If I let this go, 23. So this skyrocketed the pressure, doubled it,
Yeah.
and I cut the size in half. Equally so, if I double the size back to 10, I'm actually going to cut the pressure in half. So it's around 23. Now it's around high 11. Half of what it was. Those are the gas laws.
Yeah. But so how do we imply it?
Exactly what we just did, real world scenarios, right? So the big thing is we have obviously pressure, volume, and temperature. Okay. The other thing we have in play is moles, which we'll talk about in a few seconds. But this gas pump is moles. So obviously I can add more moles. And obviously you can see the pressure skyrocketed to 70. It was 11. Okay. I could heat it. This is obviously increasing the pressure. Now it's at 150, 180. Pressure is the essentially force over an area. So it's the collisions. The faster you're moving, the harder the collisions. Right? Like if you were walking in a crowded hallway versus running, what's going to happen?
You're going to crash into someone?
Oh, yeah. But even if you're walking, you might. And we both know how it is, right?
Yeah.
Especially on certain parts of the school. So that's Gay-Lussac's law. Okay. Now, essentially, that's semester one, so you don't need to worry about that as much. But essentially, it's this idea that the more you're moving, the more you're colliding, the higher the pressure with each other and the sides. Which is why if I lose the energy, which means you're going to move less, you can see it's moving less and less and less. And now my pressure's back down to 16. And we're at 70, so we dropped pretty good. Volume is the size of the container, so I can be really big, which lowers the pressure.
Yeah.
Or I can be really small, which makes the pressure really high. And frankly, that's the 4 variables for gases. It really comes down to this. Now, obviously, there's a few ways I can get this thing to pop, but one of the things is I can get this to increase, increase, increase. So these are directly related. You notice that as heat went up, the pressure went up.
Yeah.
As pressure went down, the temperature is going down. And which way do I want to go? And then with this one, if I reset, because the volume is the size, if I hold the temperature constant, right, these are inversed. Big, small number.
Yeah.
Small, big
I
number.
remember.
Which makes sense, right? If you squeeze something, it gets smaller.
Yeah.
And then there's the hot air balloon I just told you about. This is how they get the hot air balloon to go to the ground. They mess with the flame. It works the same way here. And that's when you can see they're both going up. Not too bad?
Yeah, not too bad.
Okay. Now, here's where it comes in a little bit more. Okay, cool. Actually, you know what? I'm going to see if I can't. There it is. I'm going to copy and paste this so I don't have to type it because this will be faster. There's there we go. There we go. So what ends up happening, right, is this idea that all these things work together. So these are the gas laws we've talked about this year. Not too bad. I hope you recognize all of them. This one is semester 1. This one is semester 1. This one is semester 1, okay?
Yeah.
Now, if you look, actually, and here's the cool part. Do you see how this is called the combined gas law?
Yeah.
Look at these 3 and put them together.
Do
you notice?
Yeah.
P1V1 equals P2V2. There it is. V with T at the bottom, P with T at the bottom, P and V with T at the bottom. Now, we don't do that one first semester because, and I'm going to be real with you, these 3 were found first, and then it was found later that, oh, yeah, you just combine them. But with the scope and sequence of the course, this is the second semester too.
That makes sense.
That's how all these work together. So to solve these, it's just cross multiplying. So those would go together. These would go together. And you're good. The only thing to watch out for, okay, the only thing to watch out for, and I'm going to write myself a timestamp. The only thing to watch out for is you cannot do Celsius. Okay, that's just not possible. It has to be Kelvin. And I can prove that to you because Kelvin is right here and Kelvin is right here. You can never use Celsius. Do you want to see why?
Yeah.
Let's see why. Okay. If we have a negative, so Celsius can be negative. And to be honest with you, that's really easy to do. 0 degrees Celsius is 32 Fahrenheit. And obviously, if we put a 0 at the bottom of this equation, we're in trouble, right? Agreed?
Yeah.
Because you can't divide by 0. That's undefined. It doesn't exist.
Yeah, no.
That's 1. Because obviously 32 degrees Fahrenheit is a real temperature. It's not that hard to do. There are places on the planet right now that are 32 degrees Fahrenheit with no manipulation. That's just what the weather is right now. That's an issue.
Mm-hmm.
And it can go negative. There are thousands of miles on this planet right now that are negative Celsius or below 32 degrees Fahrenheit. That's not good. So what ends up happening is if you have a negative, right? Like if I have a negative P, right? And I'm solving this. And again, I'm not doing the whole thing. But I think I think it'll make sense. What sign is this number going to be? If this is negative and these are positive, and these are positive, what does this have to be?
Are you negative?
Yes. And here's the problem. Or, you know what? I'm even going to do this. Watch this. We can even do it this way. Let's do it this way. Let's put the negative t at the bottom, like I said.
Mm-hmm.
Still, it's going to be negative. Because if you divide by negative, you're negative. Cross multiply, still negative. Divide, negative.
Yeah.
Can you get a negative pressure?
No.
No. And if I flip this and do the same with volume, which I can do, can I get a negative volume?
No.
No. These don't exist. And that's really the key of it. You can negative squeeze something, because pressure is essentially squeezing. You can't negative squeeze. You can't negative push, right? It's either you push or you don't. And volume is the same way. It's either you have size or you don't. You could put it in that container because it has a size, or you can't. And that's it. So when you're looking at those things, that's why you have to use Kelvin. Morning, Jesus. And honestly, that's why you have to do this. And then honestly, the ideal gas law is frankly easier. You just have to remember that N equals moles,
Yeah.
which is the gas pump I showed, right? I could add more, I could take away. And then I know you see the R values right here. So you just need to pick the correct R value.
Okay.
This one's KPA,
Mm-hmm.
use KPA. This one's ATM, use ATM. And this one's obviously a lot easier to solve.
Yeah.
And there are these on the test. Like there's 9 math problems. These are main equations. Yes, these are definitely on the test. And that's honestly gases. Does that help a little bit?
Yeah, it helped a little bit. Thank you.
No problem. You're still waking up, aren't you?
Yeah, I woke up with really bad anxiety, mister.
From because of finals week?
I guess, yeah.
You're in a good spot with me. You have a B plus. If you do well on the test tomorrow, then you're in a really good spot. It is going to come down to the final with you. I'm not going to lie, just like it did before. But you can't get a C. I can tell you that. There's no way you get a C.
Okay, mister, no. The final's gonna eat me, mister. I'm sorry. I'm not a good test taker.
Well, you're getting better at being a test taker. Don't say you're bad at something because everyone's improving and stuff. Don't do that to yourself. But we've talked before. You're okay with a B, right?
Mm-hmm.
Then you're good.
Mm-hmm. Okay.
Just show me what you know. Like
Okay.
I'm not going to judge you.
Mm-hmm.
You're safe at a B. Do your thing. And if the test goes good tomorrow, all right, cool. Maybe you have a chance. If the test is mid tomorrow, okay, then you're at a B. Then you don't even have to worry about it. Show up, do your best, show me what you know.
Okay, mister.
Not a big deal. And I am updating grades today in the afternoon. But yeah, that's really it. Genesis, we were just talking a little bit about gas laws. We kind of went into the simulation and kind of talked about a few of the things with pressure, temperature, volume, and moles. Then we just had a quick conversation about the math. And again, the math equations are given to you on the test, obviously. So you don't need to worry about that. Yeah, we could do that. Oh, that's fine. So okay, let me read your comment again just to make sure. Okay, with the laws, you wouldn't mind if I went over the laws again, would you, for her? Just to show it?
Yeah, I don't mind.
Okay, we could do it again. Okay, so what we're gonna do, we're gonna present this. And then there we go. Okay, cool. So we'll just do this again. So long story short, Genesis, there with the gases, it really comes down to and I'm actually going to get a timestamp going for this. It comes down to really four things. This idea of volume, which is the size of the container. Okay. Do you have a 2 liter of pop or do you have a glass of pop? Those are different amounts. You have temperature, which again, actually something new to mention. I didn't mention it before. Temperature is not hot and cold. Okay. Temperature is not hot. You know what? I'm actually going to do timestamp for this. Temperature has nothing to do with hot and cold. Temperature is 100% related to the kinetic energy of a given thing. Kinetic means motion, and you can see as I'm heating this up, the particles are going faster and faster and faster and faster, especially that one, which I'm surprised hasn't. There we go. So you're seeing that it has nothing to do with hot and cold. It's literally speed. And again, you can see it is flying because I'm at 59,000 degrees. If I cool it, it's going to lose energy. And as you can relate, if you lose energy, you're not going to move as much. Just like hibernation, right? When you lose all that energy, you're going to just like you guys in the morning right now. You guys are waking up and you're both like, ooh, right? You guys don't have the energy yet. You haven't had breakfast yet. You might be didn't sleep well. But you can see it's moving a lot less now. Then, if you combine that with pressure, pressure is essentially force over area. So essentially, it's the collisions. It's the collisions with each other, collisions on the sides. It's banging into each other. And you can see right now they're not. Yeah, there they hit. There's not a lot of hitting going on. But if I heat it up, because they're moving more, they're going to hit more. And that should make sense, right? If you're running through a hallway, which I used before, you're going to hit more people than walking. And you're going to feel that increase of pressure, right? Wind. Wind is when you have a bunch of air pushing on you. You feel that pressure on you. When there's no wind, you don't feel it. Perfect. And you also could add more things. Oops. The pressure was too high. Because I added so many particles, it was able to pop because the pressure was too high. So it burst. And I can prove that to you again with more. You can see it's going up way faster now. And I can still add more, or I could lose. This gas pump is moles. Moles is amount. So right now we're losing the amount of gas. Or I can gain an amount of gas. Again, it's just amount. So again, there's more things. So the pressure went up. You can see they're mixing together. This is the diffusion thing you learned in biology. And they just can play with each other. Probably going to pop. There we go. And again, how this works together is one, Boyle's law. If you squeeze something, it gets smaller. You see that I squeeze this, the pressure went up. If I make the container bigger, please notice the pressure is about 188. Now it's 60. Again, that makes sense, right? If you're squeezing something, right? I have my wife's little rainbow unicorn I got her. If I'm squeezing this thing, it takes up less space. But if I release it, you can even see it's getting bigger in my hand, correct? That's Boyle's law. And it makes sense. You know that, right? A ball outside, overnight, it's going to get smaller. It all works like that. With the heat aspect, again, if I heat something, they both go up together, as you can see. Which makes sense, right? If you're running through the hallways, you're going to hit more people than walking. You moving faster is the temperature going up. You hitting more things is the pressure going up. And it works. With this as well, and of course, the volume works the same way as well, right? If you're heating it up and the particles can push against each other, that's going to cause it to expand like a hot air balloon. This is literally how hot air balloons work. As you heat it up, it inflates, you cool it down, and you can help it land. And again, I can also do it the other way. And that is shown when you have these gas laws. And we did talk about this a little bit already. The three basic gas laws we did first semester. You did Boyle's law, Charles' law, and Gay-Lussac the first time you saw that simulation. Those were the three parts. Some people finished and did get to these two, which were for this semester. Please do not worry. These are not on the test. These were first semester. These were the first test. This was the first unit. With these two, And again, you came in right when we were talking about Kelvin, so I'm going to skip that part, but it does need to be in Kelvin. But essentially, when you combine everything, you just saw that in the simulation, right? I was just changing things like I wanted to. Nothing was stopping me. I could go up, I could go down, I could squeeze it, I could heat it, I could cool it, I could add pressure, I could decrease. That's the combined gas law. And again, you solve this by cross multiplying. And then this one is the gas pump because N is moles. And obviously, the more gas you have, that's an impact, right? You running through the hallways right now at school, right now, not a problem. No one's at school. You could go wherever you want. You could run, you could walk, you could do whatever you wanted. But tomorrow at this time, which is right when everyone's about to be released into classrooms, right? Right before your test, you're not going to be able to run as easy, right? You're going to be hitting people because there's way more people in the halls. That is moles. And the only thing to watch out for, because of the R value, you guys found the R value in class. I didn't even tell you these numbers. You came up with them on your own. You just got to use these numbers effectively when you're using the ideal gas law. Essentially, this is the KPA one. This is the ATM one. These are on the test. You don't need to memorize these. You have to use these. And that's gas laws. Does that help, Genesis? That's honestly it. That is everything. But yeah, that's everything on the test. What can I help with? Also, too, Jens, if you didn't know, the YouTube video's up from last night. Yeah, that's not possible. Oh, there's a lot of other stuff. The big thing. So you struggled on the last test. And again, part of it was you didn't want to take it. That's really it. You did fine with the moles and Stoich. Jersey.
I think it was just the equations I really struggled on.
Did that help last night then?
Yeah.
So the other thing, and we'll see what Genesis comes up with, but the other thing with last night, don't forget, is I gave you the full equations. On the test, you need to make the equations.
Okay, mister.
Which might be the next thing we talk about.
Yeah, I think I need help with that. Yeah.
Dennis, is that okay? You know what? Let's do that. That's not a bad thing to do. Okay. So let me do you've seen this before. Uh-huh. There we go. So, Genesis, are you back yet? I don't want to start without you here. She might not be back yet. Oh, cool. She's back. Sweet. Okay, let's talk about predicting products really quickly. So, that's not what I wanted. Does it work? Almost works. So when I give you an equation, okay, we're just going to do this. This will be fun. Boop. This is what it's going to look like. I'm not going to tell you this, right? That's you can figure that out. The big thing, what it comes down to is you have to crisscross everything, right? And that is something that a lot of people didn't take seriously. This is one of those topics that like we've done a lot and people just haven't put in that work with it. I'm going to be honest. Um, because as you know, every first chemical is positive, all the second chemicals are negative. This was also in every single one of those videos that you guys were doing when naming. Every single one went over this, which I know a lot of people didn't watch because those videos were a way for you to review for naming. That's why we did that unit then and not at the beginning. But again, a lot of people didn't do it. With this, what ends up happening is you're going to be putting the outsides together and you are going to put the insides together. It's exactly like foiling. And again, the reason for this is A cannot go with C. AC is not possible. Two positives, they won't even get close together. And A's already with B, so that's no change. So A has to go with D. That's the only thing left. And, pardon me, you can see the same thing works with B and C. But C needs to be first. And again, you've heard me say this in class, all dogs can bark. This is how you do pretty much everything. This is your precip reactions and your acid base. And again, you do need to crisscross all these. You got to make sure it's stable, which I'm going to talk about next. But you got to make sure you're doing it this way. It's the only way to do it. In terms of the crisscross, if lithium is +1 and sulfur is -2, right? Can I just put them together like this? Can I do this? Why not? Why is this wrong? No. Yes. Why do you think it's possible? It's all good. Yes. So it is possible because of positive and negative, but you're right. It's not balanced. You are right. It's not balanced. So that's why this isn't wrong. Let's actually say that. So this doesn't work. What does work, okay, is this. The correct equation is, and I'm going to go here. The correct equation is Li2S1. And it comes from the crisscross. The 2 goes here. The 1 goes here. This means you have 2 plus 1s. You have 1 minus 2. I literally got that from the formula. This is 0, which is correct. You also could do it this way. This is the math way of doing it. It takes a little longer. You could totally also do that. Yeah, every time. And this one, +1 minus 2 is -1. That's bad. And that's why you need to do that on every single chemical. This includes the ones on the back, of course, which we can quickly do one of those. If you had like calcium +2 and NO3, which is -1, right? If you crisscross these, Ca1, NO3, 2. Again, we don't want that 32, so we got to put it in parentheses, just like we've been doing since second quarter. And this is your answer. +2 -1 -1, because there's two of them, is 0. And that's how you figure out the products of a reaction. If it's in the middle with the transition metals, I'll tell you or give you a hint. Because those are the question marks, right? I gotta help you with those. That's fine. And yeah, that's it. Does that help? And again, that was on the last test. That was on the second test of the year. That was on the third test of the year. I need to go over this definitely harder. Yeah. Basically, did that help? Cool. What is it? What's another topic I can do? Because I know we still haven't done moles and Stoich. Um, and you have a test tomorrow. Oh, the 7 diatomics? Yeah, we can do that. Um, Genesis, what does diatomic mean? Like if you break the word down. So just break the word down. What does di mean? What does atomic mean? Because I know you know what di means, and I know you know what atomic means. So don't overthink it. What does it mean? Tri is 3. But you're on the right track. But yeah, tri is 3. Like a triangle. Okay, good. Okay, good. How many? What does di mean? When is mono? See, now you're seeing the naming right, because that naming chart's coming back. You know what I mean? Do you not remember what di is? It's all good. Di means 2. Di means 2. So it means 2 atoms. So essentially, these are the twins of the periodic table. So these elements are connected together, okay? And they are H2, N2, O2, F2, Cl2, Br2, and I2. So these should be labeled on your periodic table. So if you're looking at your colored periodic table, the symbol should look like this is what we did in class. Okay. They all should have that little corner. These are all the twins. So hydrogen is H2, not H. And those are the diatomics. So you do need to know those, because if you're doing reactions, or if I'm just asking you in general, you have to know that it's a 2. Those are special. And they're rare, just like twins, right? There's not a lot of twins. There's only 7 out of the 118. That's not a big percentage. That's about 5% of the periodic table. Under, actually, 4%. Is your periodic table labeled? So just double check it the next time you see it, okay? Because I can help you add those really quick. Not a big deal. Not a big deal at all. And that is fair game for the test because of the reactions and the upgrades, which again is this stuff. Mo Island? We can do Mo Island. So again, Mo Island and everything connected with it. Mo Island is just a way for you to go from one unit to another. For example, right? If you want to know how much something weighs, well, you need to know what it is and how much, right? That makes sense. For example, this, this is big and weighs a lot less than this other thing I made my wife, which is small, right? This is heavier. I know you can't see that right now or feel that, but this is definitely heavier than this, even though you can see the size difference. Unless I cheat and go like this, huh? But no, they're not right next to each other. So you need to know the material. This is cotton, whatever this is, polyester. This is ceramic, right? And even though there's nothing inside this, it's hollow because it's a piggy bank. It matters what it's made of and how much, right? 5 bricks weighs less than 30 bricks, you know, but 50 feathers weighs less than 30 bricks. So it's all relative to what it is. And this is how we can connect that. Again, moles means amount. Okay. Unbelievably important that we say that again. Moles means amount. Okay. Very, very important. It's not the mass, it's how much. So the way we move around, whatever I give you, if I give you some particle number, if I give you a volume because it's a gas, if I give you the mass of a given substance, a gas, a solid, a liquid, you're able to manipulate that and move around this table. So if I'm in volume, right, if I have a 44.8 liters of water and I want to know how many moles of water that is, I would start at volume. And how do I go from volume to moles? Good. Divide. It is divide. Good. Because I'm going up. So 44.8 divided by 22.4 is 2 moles water. And that's how all the 1 and 2 step problems work. Okay? That's it. That's it. You know what I mean? Just please be careful. If I have 1.8 times 10 to the 24th molecules, we'll go formula units. Formula units of salt. And I want to know how many moles of salt. Oh, yeah, there's 3. Yes. There's some of everything, actually. There's going to be some 1s, some 2s, some 3s. So, but that's a good thing. Because, Genesis, you know these. You know the 1 and 2s, right? So you're going to get 2/3 of it. That's good. It's only going to be a few questions. You know what I mean? The test is there's only 9 math problems. So, you got, a 1, a 2, and a 3. There's not going to be a lot of 3s. I'm going to tell you right now it's 3 or less. Okay? But it's not something to worry about. Get the 1s and 2s. If you remember the 3s, okay. But don't forget there's a lot of good information about, how to get the 3s too, because that's going to be on the multiple choice as well. If you get those right and you get the math wrong, it's only -1, It's not bad. But how do we do this? How do we go from particles up to here? Divide by what? Divide by what? Very good. Perfect. And again, watch the parentheses. Okay. Make sure you have parentheses around here. If you don't put the parentheses, you're going to get If you don't, you're going to get this. So you got to put in parentheses. Remember, it's one number. This right here, and I hope you can see my highlighting. Oh, you can't. Can you see that? No, you can't. If you don't put parentheses around the number, it's going to divide by 6. So if you don't put it in parentheses, it's going to divide by 6 and then multiply. Does that make sense how it splits the number? So you have to put parentheses. Then yeah, like a two-step. Like if I wanted to go, like if we do a two-step, if we want to go from, I don't know, let's go 100 grams of CO2, and we want to go to liters of CO2. We would do 100 divided by 44 times 22.4. And 44 is the molar mass. And that's how you use all of it. And honestly, like that's, you guys are good at that. Like that's not a concern. You know what I mean? You guys can do 1 and 2s, right? How do you both feel with it? And again, that's on the test. You can get those. That's not bad. Good. Talk about 3 steps. Strike time. Yes. So one of the things you'll notice that we were doing, 1 and 2 steps have the same chemical. So when you see this, right, if you have a 1 and 2 step, you're just hanging out with like green or with yellow. Like that's it. You stay green, you stay yellow. When you have a 3 step, you have 2 different chemicals. Okay. So you're at, so you pick the first chemical. What chemical do you want to be green? Up to you. You can pick any of the 4. You each pick one. Which AL one? Okay, Genesis chose KBr. Okay, you said that first, so that'll be our first chemical. And then, let's see, which one did you want with AL? There's 2 AL ones. Do you want ALBr3 or do you want the big one? Up to you.
I wanted the ALBR3.
Okay, cool. We'll do that. Sweet. So we're going to start here. Okay. And then we're going to go backwards. Totally allowed to do that. Okay. You are able to ask, hey, I need to make this. How much of this do I need to start with? Very valid question. A real life version of this would be, hey, someone just ordered 15 medium pizzas for a party. How much cheese do I need? And then you look in the back and see if you have enough. So this is a very valid question. This, oops, is going to be the start. And this is going to be the end. Now, aha, I got lucky. Oh, well, I'll tell you. It's in the question. Yeah, if you look at the study guide, it tells you. So let me show you. Let me show you. I'm gonna go right to the study guide. Okay. So So, for example, we have this equation. How many grams of P2O5 would be made if a chemist started with 8 grams? So, like, I literally tell you in the question what you're starting with, what are you ending with? So, I'm starting here, which is this, which is important, and I'm ending here, which is important. Okay, so yeah, I'm going to tell you, and I tell you every time. So here, yeah, so here, if you need 90 liters of water, okay, so starting with water. So this one's going backwards too. How many grams of that is? I mean, what is that chemical? Butane. It's butane. How many grams of butane would you need to start with? So that's going to be the end. So yeah, it tells you every time. Here's an atoms one. Here's a liter. So frankly, these three kind of do everything, honestly. And this is the linear reactant problem, by the way, just to let you know. But yeah, honestly, if you do these three, you're fine because this literally hits everything: grams, atoms, liters, grams, liters. Yeah, you can handle these three, you're good. But enough of that. Let's go talk about our problem. So, okay. With KBR, where do you guys want to start? What island do you want to start at? Particles, volume, or mass? Mass, cool. We're going to go to particles just because that's a good one to talk about for the next one, okay? So the next thing I'm doing is you just noticed I don't have all the arrows on these because you don't need them, right? Now, again, you're not going to have a double mole island, but that's really what this is. If you're starting here, it's always division going in, divide, 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 and it's always multiplication going away, times, times, times. And that should make sense, right? If you have double the amount, it weighs double. Like 2 burgers should weigh about double 1 burger. So that's multiplying. If you cut the burger in half, it's going to weigh less. Half as less. So that works as well. Which is a good thing. So, we're going to go mass. Okay. So what we're going to do is I'm going to grab all this. We're going to go boom, boom, boom. Ha, 3 booms. Get it? Okay. So we're going to just keep it really nice. You know what? I'm not going to keep it nice. We're going to go with 134 grams of KBR. And I want to know how many Formula, units. I'm just going to say particles. Particles of AlBr3. Okay? Not bad. So, here's what we need to do. Okay? First things. This is a 3-step problem. Okay? You have 100. And honestly, I'm going to show you. This is the fraction way. And the fraction way makes more sense. 1, 2, 3. Solve. Okay? Do you guys recognize the setup before I keep going? This was the cookie lab, by the way. It's like the cookies. Actually, the cookie lab was harder than this. But, yeah. So, big thing. Okay, I'm going to color code. You're going to start with 134 grams. Okay? If you're starting here, your path, right, your path is this. 1, 2, 3. So this is your path. You're going to divide, mole ratio, and then switch to particles, which is multiplying. So I know right now, okay, if I'm dividing, does dividing go at the top or bottom? Oh, divide. You already answered me. Good. Okay, very good. So that's going to be... That should be 119. Yep, 119.1. And now I'm at mole. Okay. Also, I owe you a fraction. This is the given. This doesn't count as a step because it's just the basic information. My bad on that. So here's the deal. The cool thing about all this is all the first chemical. Oh no, my wife finally woke up. Oh no. Oh no. What do you want? What? You want your computer? Yeah. Do you got $1? No. We don't have $1? We're broke?
Well, I have money in my phone.
Okay, we have money. We're good. It's been charging the whole time. Okay. Do you need the mouse? I've been using your mouse.
No, I've seen it.
Okay, you're good? Okay, love you.
Thank you.
Good morning. So we're green. The problem is we're ending with yellow. So we need to switch the step. But what's the last step? What is the last thing we have to do if we're over here? What's the last thing? Multiply by what? You are right. We're going to multiply. So it's at the top. Yes. Good. Good. And again, I like how you put the parentheses. Again, please forgive me on my spacing. So Genesis, how do you feel? You've literally just done. Look, you're almost done. Like, do you see how much you already did? That's not bad, right? So here's what we need. Also, the 119, just to show you. Is the KBR. So that's where I got the 119. So we obviously are going from green to yellow. That does not work. Right? It just doesn't work. So you need a step in between to fix this. Okay? So, morning. So what we'll end up doing is we need to switch. Do I care about green? Do I care about KBR? Okay. Wait, you interrupted me for that?
Yeah, because
Yeah, because it's Memorial Day.
my coworkers is freaking out.
On Memorial Day?
Yeah,
Is it good?
it's fine.
Okay, thank you.
Yeah.
Bye. Yeah, I want ALBR3. So this is going to work every time. This part, bottom. This part is going to go at the bottom. And then this one will always go at the top. It has to be this way because grams, cancel. Your green mole cancels and your yellow mole cancels. If you flip these two, you're wrong. This is the only new part. This is what the mole ratio is. This works every time. Every time, every problem, every reaction. Every single time. 100% no tricks. Okay. Are we doing okay? Yes. So for KBR, what's the coefficient? Like how many moles are there for KBR? Correct. Yuritsi, what is it for the ALBR3 you wanted?
Huh?
How many moles is for the ALBR2? Because this is the mole ratio we need to finish it. How many are there?
Wait, I can't see. I need to zoom in, Mister. I can't see.
Where do you want me to zoom? If I can.
No, I'm zooming in. I can zoom in.
Okay. How many moles of it? The
Yeah.
ALBR3.
2.
2 is correct. Good. And that is the only new thing you need to do. So you have an equation, right? It is balanced on the final, right? I'm not going to slow you down balancing it. So you have a given equation just like this, and you just have to do something like this. And again, this was a little harder. We have a molar mass. We have Avogadros. And I'm going to do my best. I apologize. I'm going to have to solve it with my phone, which is janky, but we'll make it work. 134 times 1 times 2 times 6.022 times 10 times 10 to the... No. See, don't even bother with your calculator. I'm going to Google. Share this. Share this. Okay, this is what we're going to do. Okay, because your calculator is that bad, right? So 134 times 1 times 2 times 6.022 times 10 to the 23rd divided by 1, because now I'm at the bottom, divided by 119.1 divided by 6 divided by 1. And what we're left with is, okay, 2.26. 2.26 times 10 to the 23rd particles. And again, I'm going to make that a little smaller. Put that there. And make it yellow. Again, multiply the top, divide by the bottom. That's how you do fractions. I don't know what they were teaching you guys in middle school, but I know they didn't teach you anything that basic. That's all you need to do when multiplying any number of fractions together. And that's all the 3 steps work. That's not bad, right? And again, like, I mean, the worst thing, like, you know this part, you know the last part, it's this middle part. You know, if you flip it, it's not the end of the world. Like, you're going to get it wrong, but like, just watch this one and you'll be okay. And you see where the numbers came from? That's not scary. Yeah. And any questions with that? And Roberto, good morning, in case I didn't say it already. The YouTube video from last night is posted. That one was kind of like redox precipitation net ionic equation stuff and some Le Chateliers for the test. And then today we've talked about gas laws, predicting products, and we did moles and Stoich. Final, yeah, all multiple choice, 90. Yeah, there's 9 math problems, but it's all multiple choice. So you can do the math at the beginning, the end. I was just telling them it's not like they're all 3 steps. So there's only gonna be like what, 1 or 2 or 3 step. You know, we're not looking to like put one heavy topic on it on the final. We want to get a little of everything. So I do have students on the math who do the ones they can do and then guess on the rest. And then the test tomorrow is 25 multiple choice only. What else can we do? Oh, good question. So with Le Chateliers, good question. 114, 40. Pressure is gases. For Le Chat, the pressure part is gases only. Everything else is solid, liquid, gas. Yeah, you just when you hear pressure, you only care about the gases. Everything else is all. So it doesn't matter. That's a good question. And let me add aqueous as well. So if we were to do a problem, let's go. Oh, let me just grab. Let me grab this equation. Let's grab this equation. Yeah. Okay, we got this. Let's make it smaller. And hey, there we go. Also, we're going to do heat on this side because we haven't done exo yet. This is exo, which is negative Q for heat. So if we do something, let's say that we, Roberto, what do you want to do? What do you want to mess up?
KBR.
Cool. Do you want to go up or down?
Down.
Cool. I'm going to put the double arrow because we need that. Okay. So if we go up KBR, okay, that means we have too much KBR. If we have too much of this, we got to use it and go backwards. And then I did mention, yesterday, you could also think of it like a slide. So in your case, if you have too much of a product, it's got to go backwards. Because again, wherever you point, that goes up. And that's very, very key. So that one's going to be good. If I say lower the heat, though, which is way over here, that means I'm getting too cold. I'm taking the energy away. I'm putting it in a freezer. That's not good. I need to heat it back up. I'm going to need to go forward to get the heat back up. Because again, wherever you point goes up. So in this one, your reactants are all going to go up. And your products are going to go down. In this one, your reactants are going to go down. And your products are going to go up. And that's how everything works but pressure. Is that good so far before we talk about pressure? Ladies, is that good? Because I know we talked about it a little bit at the end. Is that okay? It's the same old, same old. Gain stuff, use it. Get rid of it. Lose stuff, get it back. Okay, cool. So let's say we have an equation with gases. And I'm going to... I'm going to grab the famous problem. Okay. That's our famous one. I don't know why I copied and pasted in Comic Sans. So with this one, when we have pressure, we need gases. So on this side, we have 4 moles of gas. And on the other side, we have 2 moles of gas. Are we okay so far? Are we okay so far? Does everyone know where I got the 4 and the 2 from? Yeah. If there is a random chemical that's a solid, liquid, or aqueous, you just ignore it. Like, you just ignore it for pressure, move on. Okay? Only about the gas. If you increase pressure, you are going to go towards the lower amount of gas. And if you decrease pressure towards the higher amount of gas. Again, this is so it doesn't get worse. Because again, wherever you point, there's more of it. If you're pointing toward products forward, more products. You're making pizza. If you go backwards toward the reactants, you're making more ingredients. You're taking those pieces apart, you're putting them back in the containers. You know, like a Lego. That might make more sense, right? You have your Lego, you break it apart, you put it back to its individual pieces. So in this problem, if you increase the pressure, you're going to go towards the lower amount to make it better, which is this way. 2 is less than 4. And if you're decreasing the pressure, that means you need more. So you need to go to the higher amount to get more, which is that way. And that's how gases work with pressures.
Sir, I have a question on the homework.
Yes.
It's number 4, and it says adding HE, inert gas.
Yes. So 2 ways to look at this. One, is HE in that problem at all?
No.
So does it do anything?
No.
Correct.
Oh, okay.
Also, inert means it doesn't do anything.
All right.
Because it's one of the noble gases. Noble gases don't do anything. So, yeah, it just hangs out.
What about number 5, the addition of NaOH and it reacts with H?
So if you're reacting with H, are you going to gain or lose it?
You're losing it?
Correct. And then you can solve the problem now. So which way is it going to go if you're losing H? Is it going to go yellow or orange?
Yellow.
Correct.
Okay.
Does that make sense?
Yeah.
Very good.
Thank you.
And that's exactly like the lab was. The NaCl, silver nitrate, it's AgNO3, and the NaOH, all of those did something like that problem with the NaOH. Oh, sorry, my bad. So all of those lab questions were exactly like this, because there was no AgNO3 in that equation. There was NaOH in that equation. There was no NaCl in that equation. What those chemicals were doing was it was manipulating and taking away that iron or that thiocyanate. So same thing was here, and you guys could see the change. And last night we talked about that a little bit too, how if you're messing with one thing, how it could impact another. It's that kind of question. Yeah, this is your last homework of the year. And again, these are up and downs. Like, is it going up or down? So if you point at water, so let's say this problem is pointing at water. If you point at water, it goes up. Like, pretend. Right? If I'm going this way, I'm pointing at O, because it's over here, goes up. Again, whatever you make goes up. Yeah. Did that answer the questions with the Chateliers?
Yeah.
Sweet. And again, that's on the test a little bit for tomorrow. And I am curving the test if I haven't told you yet. I know I wasn't there. I'm going to curve it. What can I do next? We got about 20 minutes left. I'm pretty pleased with what we've talked about. Is everything good for the test? Because again, we've talked about a lot of it, but not all. Le Chatelier's is a big part, though. We talked about equilibrium. We talked about Le Chatelier's. We haven't talked about rates, but I'm hoping that's not too bad. There's no Hess's law, so you don't need to worry about Hess's law. Oh, activation energy? We can do that. I'm going to be right back, though. I think my wife called me. I'll be right back. From what? Yeah, give me like cactus waters. Yeah, give me like a cactus water. That'd be fun. And we're gonna walk over there. Yeah, we're gonna walk to Jewel. Then we're gonna walk back. We have adventures. We're going on an adventure. Oh, okay. Activation energy. Boop, boop, boop. All right. Okay, let me get a chart. All right, we're gonna do. Oh, that's not gonna work. Okay, we got this graph, and then we've got. Yeah, there we go. Okay, so activation energy is this. Is how much energy to start a reaction. So on both of these charts, your reactants are going to start here. So your reactant starts here. Your reactant starts here. It has so much energy. Let's say this is 100. And let's say this is like 20, just to make up some numbers. Your products, right, are going to end either higher or lower. Okay, let's say that this is 50, and let's say that this is 50. So the activation energy is when you need to see how much you need to get started, which is this very top point right here. Every reaction needs something to go. If it doesn't, it's called spontaneous. That's an AP chemistry topic. But in terms of this, every reaction needs a little bit of a push. And that's it. So they both need energy. This one loses energy. So this one's the exothermic one. And this one went up. It gained energy. Specifically, this one gained 30 joules. Joules is energy. And this one lost 50 joules. And yeah, that's kind of it. Not too bad. Oh, and then I might ask you how much energy that takes. My bad. I probably should have did that. So this one will say like it's 300. This one, let's say, is 80. So for this one, the activation energy is positive 200 joules. Please forgive my handwriting. And this one is, and the EA is activation energy. Believe it or not, that's the abbreviation, is plus 30 as well. Is that okay? Not too bad?
Wait, how'd you get to 200 and 30?
Oh, so with the 200, it was at 100 at the beginning, and then it went up to 300. So 100 up to 300 is 200, and then this one, oh shoot, yeah, it should be 60. Is that what sorry, you were probably thinking that. My bad.
Yeah, kind of confused me.
Sorry, you're right. Yeah, it's 60. Sorry, 20 up to 80 is 60. Yeah, I would never ask you like blue to green. That's not a term. And yeah, these diagrams are on the test tomorrow. EndoXO is already on the test. We've gone over that. That puts things in a pretty good spot. I'm just checking some things. And anything else? And again, the test is curved tomorrow. I'm going to curve it. I'm just debating how much. It's going to depend on something tomorrow morning. Anything else? Oh, percent yield? Absolutely, we can do that. Yield. Yields. Okay. So you got theoretical yield, actual yield, and the percent yield. Okay. Theoretical yield is what should happen. Actual yield is what does happen. And percent yield is how good did you do? Okay. These are all connected with limiting reactant problems. Which are 2 3-step problems. Okay. So essentially, what you end up doing is, and actually, let me do this. Yields and limiting reactant. Okay, cool. Sorry about that. So let's say this. We have an equation. Okay. Okay, we get this. Okay. 40 grams of A is 30 grams of C. 40 liters of B is 28 grams of C. Which one's going to run out first, A or B? Are you going to run out of 40 liters? Or are you going to run out of 40 grams? Are you going to run out of A or B? Okay, you're the tiebreaker. What's going to run out first? It is B. So what ends up happening, Genesis, is when you run out of B, you're at 28. Is this reaction going to work if you run out of B? Like, can you make pizza without cheese? Really? No, right? So what ends up happening, you're never going to get to 30. You're done. You're done at 28. You'll never make 29 grams. You'll never make 28.1 gram. You are out. And again, the linear reactant is what runs out. So B runs out first. Okay. So your theoretical yield is 28 grams. That is literally from the Stoich. Now, in lab, you make 8 grams. This means the actual yield is 8 grams, which is terrible. So, what does all this mean? Oh. So, your percent yield is equal to it is always actual divided by theoretical and again it's a percent, so times by 100. And it's literally just like your score on the test. It's what should have happened. Okay. On your test, it's going to be out of 25 points, right? The actual yield is U, which goes at the top. And the percent yield is like a grade. And I swear to you that this isn't all on me. Come on. So for this one, it's going to be 8 divided by 28 times 100, which is 4 14ths, which is 2 7ths. Oh, that's not good. Yeah, 28.6%. That's terrible. So, yeah, that didn't go very well. And that is all of the yields. So that's coming from a linear reactant problem, which is again from Stoich. Because again, we're going A to C and B to C. That's Stoich. So you got to just compare the two answers. And again, you don't have to do anything in lab, of course. You guys will be given that. But this I did all the time in college. Like this is when you're trying to figure out what's going on. This is very, very, very useful. And I think this is probably a good place to stop the video. So I'm going to stop that.